All right, welcome to class today. Sorry that I missed last week. Um, Hopefully you were able to download watch the video that's on YouTube. So here's this week right here we're talking about water and surface flow. So um, I'm gonna just talk for a few seconds about what I'm going to do today. So um, today we're not going to present too much new material. What I want to do is talk about this a little bit, make sure everybody understands the concepts, see if there's any questions. That'll go pretty quick, maybe 15 or 20 minutes. I'm not going to go through the entire lecture, but I will download it and talk from there. Then the main thing that I want to do is, and this will take a little while, is talk about the lab and a few of the issues with the lab, basically, and actually use it as an opportunity to introduce what will be my discussion of the test. So I want to have a review session, talk about what's going to be on the test, and the lab is actually kind of a part of the test is working out some of these GIS raster problems by hand, and so the lab does have that element to it. So we can see how we can answer the questions, or how we need to answer the questions, and you all can answer questions. So that's the order. Hopefully you had an opportunity to read this. This is the paper, the academic paper that it's an old academic paper, but it's the academic paper that 1988. So we're going on over 30 years there. But it's the paper that these concepts are based on. So I'm going to download this lecture here real quick. I should have downloaded that already. And just show a few slides here. I don't know why that's taking a second. Am I not connected to the internet? I'm connected. Anyway, I'm pretty sure I already downloaded it earlier, so. Hopefully, are y'all still there on Skype?
Yes, sir.
Yes, we're here.
Okay, just making sure because the internet seems to be going a little slow here.
We're just not getting on like our big screen up front. Nice version.
Oh, okay. Like you don't see the screen.
Oh, we can see like on our personal screen that we're sitting, but not on like the big screen that where you usually present if you're here.
Where is it? Is the screen up there at all?
It's up to the right, like on the right TV in the corner, but
not.
I don't know if that.
There is a way to switch those, but I don't know the button,
I think it's okay.
the buttons to press to do it.
I think it's fine.
Okay. Yeah, they're. All right. Technical difficulties. Yeah. Yeah, I don't know if everybody. If there is anybody else that wants to be on there, let me know. All right. So in order to do the lab, it's important that we understand two concepts, and these concepts are concepts that, well, the general concepts are what some of the things will be on the test. Okay. So anyway, the two concepts are, first of all, since this is a process that requires running multiple tools, the first concept is understanding what tools are to be run in what order. And then the second concept is what the tools themselves are actually doing. Over the last few weeks, we talked about calculating slope, and slope is a measure of how things are changing. But the first tool, well, actually, before we start talking about the tool, let's do this a little bit backwards. So we've got this diagram here, and I forgot whether I have a better one. I probably need to update this a little bit. Anyway, this will work. This one looks a little old. So we have our original DEM, and the purpose here is to it's kind of like, what if water fell? We're really talking about a model. What if water fell on our model? Where would it flow? And where would it accumulate so much that it created rivers and streams? That's a question we're trying to answer this week. And so there are actually a lot of different outputs, but in the lab, we're mostly concerned with this flow accumulation and watershed outputs. And so in order to do that, we run flow direction, and optionally, we could see if there are any sinks after we run flow direction, and then fill them. That usually be the best way. For anybody that watched the video, what if we don't fill the sinks? What will happen? What if we don't? If we have a DEM and we're trying to figure out how water will flow off of that DEM, what's the purpose of filling sinks? Does anybody remember from the video?
So the water doesn't get stuck in the low spots.
Right, exactly. So we're not directly monitoring like the water moved from this cell to this cell to this cell to this cell. The first step is to find out which direction the water would flow out of every cell. And so if we don't fill the sinks, then there will be multiple cells that all flow into the same cell, and that's what's called a sink, and then there's no outlet point. So in the video I talked a little bit about why there could be sinks, but there could be sinks because there actually are sinks in real life, and there also could be sinks because they're actually depressions that already are filled up with water. And in either case, it's more likely that the water will eventually flow out of a sink area. And so you can either calculate flow direction and then see if it has any sinks and fill them up, or you could just skip right to this step and fill the sinks, and then rerun flow direction. Okay. Once you have flow direction calculated, there are a number of different outputs you can do. Flow direction is the primary output. It is, every cell is given a value for the flow direction raster. And what does that value represent?
Right.
Yes, the flow direction, meaning the direction that water would flow out of that cell to one of its neighbors, to one of its 8 neighbors. So it could either flow north, south, east, west, or northwest, northeast, southwest, or southeast. And it is a model of reality. I mean, it may be that in a very low slope area, like a marsh, that it kind of just oozes out and it goes in multiple directions. So, I'm sure there's been many studies that look at the effect of using this particular algorithm. It's called the D8 algorithm, to calculate flow direction that does it work in different areas as well as other areas. Okay, so then we can create a watershed or flow accumulation, and even calculate flow length. And these are all things that are useful in modeling. What is a watershed? I'm doing a little quiz here, so you should have watched the video. What's a watershed?
It's where all the water from like the different areas all converge to the center. It's like basically anywhere water's going to fall. It's said that as long as it's going to be in that encompassed area, it's the watershed for that area.
Okay, it's all the area. Yeah, it's an area. That's an important key thing. The watershed is an area that all flows to the same location, right? Or the same river system, whatever. It's the upslope area. So this is flow length. It's the length of the and it's based on a pour point. So a pour point is used to define a watershed. A pour point is the location that we specify as a point, and then the watershed is all of the area that is upslope of that pour point. And flow accumulation can be used to do the rivers and streams. Like this is the flow accumulation surface. So we're getting flow accumulation there. And the higher flow accumulation occurs in areas that are more likely to be rivers. So you can use this to answer questions like where rivers might be. The United States has done this for the whole United States. They've run this on the digital elevation models that they collect. It's called the National Hydrography Dataset, the NHD. So you can look at it. I was hoping that there'd be a better picture. There's a better picture. So it's all vectorized. So they took all the flow accumulation values and turned them into lines, and they have here they have different streams that are created from the flow accumulation lines, streams, and they also have watersheds, and they call them hydrologic units or HUCs. That's one of the things that they've done. But if you have a particular study area, it's often best to do that yourself. Another thing that you can do is with this data is once you have flow accumulation, you create streams. You could create stream order maps. And this isn't stream order, but that's something that you could derive from the flow accumulation. All right. Okay, so this process, and I admit that graphic isn't the best. The graphic that I showed before, I can't find it now. Sorry. That process that I found there, I can't find it. All right, that process is the process that we want to execute in the lab. And in this lab, we're going to work it out by hand first, and then we're going to work it out by doing it in ArcGIS. Okay. So here's an example of how you might work it out by hand even before we had a GIS system. We had a topographic map. One way to sketch a watershed boundary is by following the drainage divide by intersecting all of these contour lines at perpendicular intervals. And you could kind of tell, okay, well, if I want to find out all the area that flows into this, then I have to go up to the top of the ridge lines and around and back down to the ridge line, so I can delineate that by hand. But if we were to do this with numbers, with actual values, we could do that in a very simple way. I did it with what I'm having you do here is just a small little set of cells. So I've got the data here. You can download the data. I've already downloaded the data. I'm going to open up the file. I already downloaded the file, actually. Well, you certainly can put it wherever you want, but a lot of times when you actually go to execute things in GIS, the USB's read-write capability is about 20 times slower than the hard drive. So if you're going to do something that requires a lot of read-writes, it's better to write it to the hard drive because you're going to take a lot longer going with your USB drive. But the way that I've done it in the past is I actually copy it locally, and then if I want to finish, I would take my data and pull it off of there and put it on my USB drive. Then I can even move to another computer and put it back into a drive. I can actually show how we do that. So I'm gonna close this down. I'll do that when we move on to the second part, which I'm not going to spend a whole lot of time on this first part, but because I want you to calculate these values out by hand. Okay, and they aren't difficult, but we do need to do that. First of all, one of the things that we're going to do is ignore all of the outer cells. Okay, I just put numbers there for fun to show you that there were values in the outer cells. When you're doing water modeling, it's always best to ignore the outer cells because you don't know if this cell perhaps flows this way, whereas this cell, well, that's not a good example. Let's say, there's this one right here. So there's a value of 53 here. We don't know for sure if it flows into this cell or if it flows into this cell over here because we don't know what that value is that's right next to it. Like, what if that's 49? Well, then that's where it is. So the way that the GIS software models which direction it is based on what? How does it model which direction? Do you remember from the video?
Based on the surrounding squares.
Based on the surrounding squares, but what's the kind of the basic algorithm for finding out which direction the water flows? Remember, it's called the greatest. It's not called the greatest, but it is the greatest drop. The local drain direction is the direction of the greatest slope. Okay, so the direction of the greatest slope. So for each of these values, and you don't need to find any of these values, you only need to find these. You need to calculate the direction, the lowest direction. Now, you could go right into that and find out that there's some sinks, or you could actually find the sinks first. So that's what I said here. Label the pit cells with the elevation they would have once the pits are filled. So you don't need to calculate every single slope value to figure out that there's going to be some pits, right? So, for example, does anybody see a pit?
Like 36.
Yes. So you've got 36. That's a pit because every value around it is bigger than it, right? Now, what about, is that the extent of the pit? Is it just one cell?
No, it's also 37.
Okay.
It's like the top of it.
Right. And how do we know? How do you know that?
Because it has the volume has to reach 37 for it to spill into another cell.
Right. So if we change this to 37, then it would flow in that direction.
Right.
Because it would
equal out.
It would equal out. All right. Now though, if this is 37, what direction will it flow from here?
40.
40. But will it flow to 40?
39.
Or 39. But will it flow there? How can 37 flow down to 39?
Oh, no. I was thinking, I got backwards. But no, it can't go anywhere.
It can't go anywhere, so it's still a sink.
Right.
All right? So when you label the pit cells, you're labeling these two cells. And so in order for them to not be pit cells, what cell do they need, what value do they need to be raised to? I'm not talking about exponents here. What value do they need to be increased? We need to fill them. We're going to fill them manually to what value?
39.
Yes, they need to be filled to 39 in order for it to flow into this direction, into that direction. Okay? So that's like the first step. So that once these two are filled to 39, you can figure out which direction all of these would flow. Okay? And you don't have to explicitly calculate the slope every single time to figure out the direction. Sometimes it's obvious, but sometimes there's a question as to which one is is more obvious. I didn't make any exactly equal to each other. I tried not to make any that were exactly equal to each other. So that shouldn't be a problem. But like, for example, this one's 67. Is there any question which cell it flows into? This one right here.
No, 47.
The 45, you mean?
Yeah, 45.
Yeah. Now remember, it's not going to flow into any of these. All these are going to flow. Oh wait, you're right. It can flow into one of these, but it can't. But from there, it just flows off the map.
Right.
Okay. So yeah. So you said 47, but yeah, you were actually wrong because you didn't notice this says 45.
Right.
So this one is actually flowing in this direction. Do you remember what the value is for that? What the coded value is for southwest, southeast? What's that? Is it 2? It's right here. So yeah, it's 2. Good job. So then you would put 2 right here. Oh, I'm going to hit enabled editing. So then you put 2 right there. Okay. Right. And then we move on to the next one. So here we've got a bunch of values. Okay. Which one's the biggest drop?
36.
36. Yep. So it's the same, right?
It's going to be
2. And so on. Now, there are a few. Well, actually, this is 39 now, by the way. But it's still that direction, right? So we could, if we wanted to, we could go ahead and put something like this, just so that we remember as we're typing it out. But that's what that value really is after it's filled. Okay. So yeah, that's the right value for there. Now there are some that might be a little bit harder. Let's see. Well, for example, 45. That looks good. Well, here, this one might be harder. 52. Is it going to go? No, that's going to go to 40. 43. That's going to go to. Oh, well, that's 39 or 38. It's just going to go to 38. All right. Well. Oh, here's one. This one right here, 42. These are 39 now. These are both 38. So which one is it going to? That's 36. Oh, so it's going to flow there. Okay. I'm trying to find one where it might be a little bit difficult, but you should just be able to plop them in. But if you ever have any question, the first thing to do is calculate the actual slope value. What is the slope from here to here? Remember, it's the rise over the run. So the slope from 36 to 40, or 39 to 40. Oh, that's yeah. Okay, the slope from, let's say, 45 to 40. What is the rise? What's the difference in z value? 5, right? So the difference in z value is, so if you ever had a question where you couldn't just spot it instantly, what you should do here is calculate the actual slope. So 5, and then what's the run from 45 to 40? What's the distance, basically, from the center of this cell to the center of that cell?
100 meters.
Yeah, is that what we gave?
Well, I mean, above it says grid cell size 100 m. So
yeah, right there. Sorry. All right. So 100. So we say 5 divided by 100. Whoops. You could do that on a calculator, but I'm going to do it here just so I can keep it. So 5 divided by 100. That is the slope from here to there. What about the slope from here to here, 45 to 42?
3 over 100.
3, but it's actually not over 100. It's the center of this cell to the center of this cell is what?
It wouldn't still be 100?
No, because the center of this
it goes at an angle?
it goes at an angle, so the difference is
150.
well, it's 100 times 100. I mean, sorry, it's 100. So the formula is a squared plus b squared equals c squared, right? So we need to take both of these values from the center of this cell to the center of this cell and the center of this cell to the center of this cell. That's always going to be 100 in each case. So it's 100 times 100, which is a big number, and then 100 times 100. We add those together and take the square root of that value. Okay. Now, if you'll SQRT the square root of 2, you can just trust me for a second, because these are all what we would call right angle triangles, it's always going to be the square root of 2 times the cell size. It's going to work, the math is going to work out, because if this was 1 and this was 1, this would be the square root of 2. So all we're doing, we're going to scale it up by that number. So that's 141. So this would be 3 divided by 141 there. Okay. So now we can see which one has the greater slope. Does this have a greater slope than that? Which one of these numbers is greater? That's like
5%.
Yeah. It's not a percent. It's a fraction. It's a ratio.
Okay.
But we can. But you expressed it as a percent. Never mind. That's correct. So 5% or 2%. You could express it as a percent. Yep. Sorry, I shouldn't have corrected you there. So it is 5%, or 0.05. 0.05 is greater. So this is greater slope than that, and we can kind of see that. I mean, that makes sense, right? What if they were both 40 though? Just I want to show you. If they're both 40, this would be 5. And sorry, that would be 5. So if they were both 40, which one would have a greater slope? Well, it'd still be that one, but it's important to recognize that it would be that one, not this one. That's actually not as steep of a slope as this. And so what would this one be coded? Here, it's actually going to be coded this direction, right? 39. So what would that one be coded? In that case, it would be coded 1. But if it had gone south, it would be 4, and so on. So anyway, you fill that out. You fill this out with the right values. Okay. And then we move on to the flow accumulation grid. Once we have the flow direction grid, we're going to calculate the flow accumulation grid. And again, we're just going to ignore the values outside of the edge, because we're going to keep the edge up. But if both of these cells flowed in that direction, then you could see how this cell right here and that cell right there would both get values of at least 1. So it's all of the cells that are upslope of this cell. Okay. It may be that this cell flows south. If that cell flows south, then we get a value of 2, and so on. If this cell flows into this direction, we'll get a value of 3, because this cell, and this cell are all flowing into it. So in this one, you're going to put the number of cells that flows into that cell. Okay. That's how you answer that question. All right. And then finally, the last question here is that we want, well, it's actually not the last question, but sorry, the next question here. If we were to define channels as those cells with flow accumulation values over 2, which cell would be chosen? So anything over 2, you're going to shade in, circle those cells. So you're going to circle them, not shade them in. You're going to circle those cells over 2, right? And then the next thing you're going to do is using this. This represents a different grid that you didn't have before, okay? And so what you're going to do is the grid cells here represent how much runoff there is in every cell. So from a particular rain event, or maybe this is a yearly runoff, this represents the, based on the precipitation, sorry, this is the precipitation, and based on this formula, we're going to calculate runoff. So we're going to take the precipitation value, multiply it by almost half. We're going to multiply it by 0.15 and subtract 336. So how would we do that? In other words, I want to see the result of this formula in this map.
So it would be like 900 times 0.51 minus 336, and then that's what we need
Yeah.
for that.
Right, and again, you don't need to calculate. I've just put values out here for fun. You don't actually need to calculate those values. Only inside the white area.
Okay.
So it's only these, what is that?
970. Yeah.
15 cells. So yeah, you put 970 into that formula, and you get a number. Okay, so the way I would do that is I'd kind of come back to Excel here. 970 and say equals 0.51 times 970 minus, what was the 336. I have a value of 158.7. I put that value right there, 158.7. And I do that for all of these values. Okay. You could, if you want to do this quickly, you put in 960. Then in Excel you can fill down. So that'll tell you what the value is there. Then you can copy that over, or you just put in a new number, 958. Copy that over, and that's the one that goes right here. So fill all those values out, all the whites. Those are 15 of them. So you're doing this formula 15 times. Okay. What type of operation is that, by the way? So this is where it kind of gets into reviewing the test. How would I actually do this in ArcGIS? How would I do this if I had this cell and I wanted to calculate runoff from this? What would I do to get that to what would I do to get this cell value? And if I wanted to test my work using ArcGIS?
Use the raster calculator.
Yeah, I could use the raster calculator, or I could just run the times tool first, multiply them together, and then do the minus tool and subtract it. Okay. But what type of operation is this in terms of zonal, focal, or local operation? I'm going cell by cell and calculating value. Local. Yep. Exactly. Good job. So that's a local operation because I'm going cell by cell. I'm not looking at the neighbors. So if I should have asked that up here. Flow direction is what type of operation? A local, zonal, or focal operation. Calculating flow direction from this grid. Nope. It's a focal operation. Yep. Good job. So a focal operation, because it looks at its neighborhood. Focal and neighborhood are similar. So every cell, I'm looking at my neighbors and I'm assigning a new value. That's a focal operation, a neighborhood operation, a neighborhood or focal operation. Okay. All right, and then we haven't done a zonal operation yet, but we're going to do all of them here. So this is a neighborhood operation looking at flow direction. Flow accumulation is kind of like pretty much a global operation. You're looking for every single cell that is flowing into a particular cell. Okay. And then just doing a simple raster calculator function like this is a local operation. And then finally, the last thing you're going to say is if these are 100-meter cells, calculate the mean annual stream flow draining out of the outlet cell B in meters cubed per year. So this is if these represent the mean annual stream fall. Okay. So how would I get that information? what is the mean annual runoff for that particular time? Well, do all of the cells flow into this cell? I don't know if anybody's worked that out at this point.
No.
No, they don't flow into that cell. They don't all flow into that cell. So first I need to find out which cells flow into that cell. In ArcGIS, I would do that through running the watershed tool. So create a watershed. But you're going to do that manually. You're just going to delineate. You're going to draw a little box. I don't know if this is the right box, but I'm just drawing a box around all of those cells that flow into this cell. And when you do that, what you're going to do is you're going to calculate the total amount of runoff that's going to reach that cell. So that in ArcGIS, we'd implement that as a zonal sum operation. Okay. However, remember that the cells are 100 meters by 100 meters. So your zonal sum, if you think about it, the values that you get here, what are the units going to be in terms of runoff? What are the
millimeters per year.
What's that?
Millimeters per year.
Exactly. They're going to be millimeters per year. So if they're millimeters per year, that's a linear distance. Okay. So the way we're modeling that is that we got, what was the first number we got? 150 something millimeters that fell onto that cell. So what we're saying is, not fell off the cell, flowed off of that cell. So it's as if the cell was 158 millimeters deep for the whole cell. Okay. And so to calculate the volume, we need to calculate 100 by 100 times the cell size. Or alternatively, we could just add all the cells up that are inside the watershed, and then multiply by 100 by 100. So we're going to do zonal statistics, and then we'll get the zonal sum for the watershed, and then finally we're going to take that zonal statistics number and multiply it by 100 times 100, which is, what is that? 10,000, right? So we're going to multiply that by 10,000, and we're going to get our answer. Oh, but then we have to convert that from millimeters to meters. So we have to divide that by another number. Okay. We could just look that up, although it's just getting some zeros out of the equation. All right. There's probably a few different ways we could actually get that. We could do it before we did the cell size, or so on. Actually, okay. Let's actually talk about how to check our work here, because this changed really recently. So ArcGIS just upgraded their software to version 2.5, and I installed it in the Hattiesburg campus 2 weeks ago, and yesterday when I was down for my other class, I installed it on all the devices here. So if you're working on any of the lab computers, you're using 2.5, and it doesn't actually have the tool called ASCII to raster. That tool disappeared. Okay? And thanks to, it was Shar Aaron that pointed this out. But if you use an older version, you can still use ASCII to raster. But if you're not, you need to use the copy raster tool. And ESRI did a weird quirk that makes it so that it's kind of hard to run it that way. Not hard, you just have to know what you're doing. So I want to point that out. So I'm gonna do that right now as part of the video here. Good, I'm recording. Okay, so the way that you turn this blob of text into a raster is that you copy it into Notepad. So you just open up Notepad. I've got Notepad++. I don't know if all of them have Notepad++, so I'm just going to do this in Notepad. You paste it in there. This is an ASCII representation. Occasionally, you will find websites where the data is downloaded in this format. Plus, you can always use it to create your own small raster data sets. It's a pretty simple format. You do need to specify all of these keywords. So you need to specify the number of columns and the number of rows. And any white space, the way the spec is written, I'm not sure if USRI will always agree, but any white space in between numbers will constitute a new record. So theoretically, you could just have all of the ASCII values, like, because the carriage return counts as white space. So you could have them all just lined up, you know, because what's 7 times 5? 35. So you just need 35 values with white space in between. So the number of rows and columns is needed because this doesn't actually specify rows and columns according to the way that the spec is written. Okay? So you need to specify the rows and columns, and it'll turn it into that. And then you need to specify the corner, like where the corner will be in some coordinate system. If you don't specify a coordinate system when you create it, it'll just assume that it is a latitude and longitude coordinate system. So this will be 0, 0 at the intersection of the equator and the prime meridian. Anybody know where that is? Where do the prime meridian and the equator intersect? It's not a place, but it's in the middle of the Atlantic Ocean. So don't be surprised when we import this. That's where it ends up. But this is just for fun. So then the cell size is right there. And then finally, you have to specify a no data value. You can specify whatever value you want. If I specified 47 as no data value, it would turn that into no data as it was importing it. Okay. All right, so I'm going to hit File and then Save. Actually, before I save this, I'm going to go ahead and create a project. So I'm going to go into ArcGIS Pro, and I'm going to save it like into the project. I should have had ArcGIS Pro already open, but I didn't. All right, so I'm going to create a new project. I already did this once, but just to test why it didn't work, but I'm going to do it again. So I'm going to call this project. I'll just call it Hydro Lab. Okay. Then I'm going to hit OK. I'm going to copy this location here. All right, now if you wanted to make it like really easy for you to make your whole project portable to use on any other computer, probably the best idea, and the reason that I copied that path, is to put the data that you download. So here's the data that I downloaded, the Hydro Data Lab. I downloaded that. I'm going to put that data inside of the folder. So I'm going to copy this data, and I'm going to put it in the location, which was C. It's in Documents. It's C Users Documents. You just need to remember where you saved it. ArcGIS Projects. I call it Hydro Lab. There's Hydro Lab right there. Okay. And so it might be better to have gotten the whole folder, just so that the data itself is in a folder. So let me get that. So I'm going to copy this into that folder. Now this is a little different than like other times I've shown it. I've said, oh, you can just in ArcGIS Pro, you can just add the reference to it as a folder, and then find it wherever it is on disk. The advantage to doing it this way, and the reason why I'm showing this is because the question that Brittany asked. The advantage to doing this is that I've moved it physically into the folder. And so now if I use any of the information here and I make a map with it or whatnot, then I can just take this whole folder under projects, this whole HydroAd folder, and copy that and put it on my thumb drive. And then I could move to a different computer and copy it off of my thumb drive and then open it. Copy it off my thumb drive, then double click this and open it on that other computer, and everything will work. Okay? Because it's not looking for data in two different parts of my computer. It's all stored in that. Everything in that projects folder is referenced by relative path names. So in other words, it says, oh, your data was two directories down from the main project folder, one directory up from the main project folder. Okay. So that's how ArcGIS is storing your data. Just kind of a sidetrack there. But because I put the data there in this HydroLab folder, it's HydroLab, which I guess is not horrible, but I'm going to put this this notepad text data there. So I'm going to go back to here and say File, Save As, and I'm going to go to that location. I copied and pasted it because it's hard to remember. Okay, and then I'm going to name this one. I'm going to change this to all files. And then I'm going to name this one. Which one was this? Did I copy and paste? I copied and pasted the elevations. So I'm going to name this elevations. In the lab, I named it elevs because I was lazy, I guess. And then you need to say .asc and hit save. So once you do that, that's saved in that location. So I try to describe this here. So you can save it as a file, make sure the extension is ASC. All right. Now we need to actually run it in copy raster, but you'll see there's a problem. That I think ESRI, it's basically a bug, right? It's not a big bug because you can still do it, but the problem is that it won't let you see the file you just created. So I'm going to type in copy raster and execute this tool. All right, so when I do this, right here, if I press this little button to browse, and I try to find it, if I go to folders, because it's going to be in there, I have to hit refresh. Oh no, it's in there. What's that?
What's the extension you said?
ASC.
ASC.
Yeah. So see, I'm in the folder where I know it's saved. I know it's in here because I put it in there, right? Even if I hit refresh, it won't show up. So ArcGIS forgot to include this as one of the supported types when they made copy raster be able to copy ASCII raster files. So it's not there. But they did make it so that you can still execute it. So what you have to do, one thing that I might do is click on one of these other files that's in the same folder, and then I made this way too big, didn't I? Whoa. Click on one of those other files and hit OK so that you know it's in the same location. And then you need to click into the box and rename it elevations.asc. You need to type in the file name. And you need to spell it exactly right. See, it's right there. You need to make sure you spell it right both times and they match. Otherwise, you're going to get a problem. But see, now when I click off of this, it doesn't give me, like, if this didn't exist, it would give me a little X. If you spelled it wrong or something, it's going to give you a little X that is going to tell you that it doesn't exist. Now, this is where it's going to put it. I suppose that's as good a place as any. It's in the geodatabase. It's basically up one here. It's inside this geodatabase. But I'm going to call this, I'm just going to call this worksheet DEM, because that's what it is. It's the raw digital elevation model from the worksheet. And I can go ahead and leave everything else the same. There's nothing else I need to change. It'll figure out the pixel type. The default will be good enough. So I'm going to run this. And once I run it, it doesn't look like anything's happened. It doesn't zoom into it. But I can, if I right-click on it, I can say zoom to layer. If I zoom out, you can see that it is in the middle of the Atlantic Ocean. Well, not the very middle, but it's at 0, 0, which is where I told it to go. But it doesn't really matter. Okay? I'm just using this to check my work. So I need to execute each of the tools in order to get this to work. Okay. So there's my first tool. There's my first layer. It's the elevation layer. I can check the values. I can inspect the values in it by clicking anywhere. So let's click this one right here. See, that's 67. That corresponds with the second row, second column. And if I go back over here, 67 is the second row, second column. I just brought that raster in to ArcGIS that way. So I have the ability to have a raster data set. Okay. Now what's the first step that we want to do to verify our work? We want to follow the workflow through that we just did by hand. Well, that you may or may not. By the way, I made this due. This isn't due till next week. Okay. So, what's the first step here? It's not explicitly stated, right? We have flow direction. That's actually the second step. What do we need to do before we even do flow direction? What did we do up here? Yeah, we filled in the sinks. So we need to execute that tool. Fill. That tool is fill sinks in a surface raster to remove small imperfections of the data. That sounds like what we need. There actually are a couple different versions of that tool, 2 different versions. They're just different licenses of the same tool. We have a license. I know we have a license spatial analyst, so I'm going to select that. And oh, that's actually a good point. I did it by accident. I meant to execute the tool, but did you see that? Fill. If you click on this little button right here, it actually opens the. If you click on this text, sorry, it opens the tool in the toolbox to show you where it is in the toolbox. If you click this, it just goes ahead and opens the tool. So I clicked this by accident, and see, it shows me that they're all in hydrology. In fact, a lot of the tools that we're going to use are in this hydrology section. We're not going to use all of them today, but you could experiment and use some others on your own data. We're going to use fill first, so I'm going to double click fill, and then I'm going to choose the digital elevation model, and I'm going to rename this. Instead of fill worksheet, I'm going to call it worksheet DEM underscore filled. Okay, and then I'm going to run that. Oh, before I run it, what would the Z limit do you suppose? I mean, what does it sound like it might do? Remember, we're filling sinks. Anybody got any ideas of what it might do? You can't be wrong, because I'm just saying.
Tells it where the upper limit for the fill is.
Yeah. So it will, if a sink is more than 5 units, and you set it at 5, it won't fill that sink. Okay. So it'll assume that. And what that does is, when you're doing your water modeling, what you're saying is that depression would never fill up. So water will always flow into that sink. So it is an acceptable thing in a model to say that there really is a sink there that would never fill up. And in some cases, though, you want all sinks that are 1 or 2 meters to get full, to be able to get full, because if there's enough rainfall, even if there's not 2 meters of rain, if there's enough rainfall and you have water flowing into that, it's either going to fill up or it's already going to be full and spill over and continue on. So anyway, that is a value. But we're not going to change that value, but that's exactly what it means. We're going to leave that the way it is. We're going to hit run, and then we're going to have our filled DEM. This looks pretty colorful right now, right? And why does it look like that? Well, it's because of the way it's symbolized. This is symbolized on a continuous scale. This is symbolized as a discrete scale, and just by default, it'll do that. But we could see this value right here is 67. Okay, that's not that interesting. But remember, we said that it would fill this sink right here. So remember what we said that the values would be? Because we're checking our work. Yep, 39. So we click that, and look, it's 39 now. So it did it just as we predicted. We followed the algorithm, and we got the same result as ArcGIS. Okay. I'm going to go a little bit of sidetrack here. What happens if I wanted to find out where all the sinks occurred, and I wanted to find out how deep the sinks were? What could I do? What operation could I run that we've talked about this semester that would show me every cell would have the depth of the sink? So it would be a 0 if there was no sink there. And it would be a 1 if it had to fill up, 1 unit. It would be a 2 if it had to fill up 2 units, and 3, and so on. How could I get that? I can get it from just the 2 data sets that I currently have. Sorry, somebody on the Skype said something.
I was thinking maybe a condition, but Aaron said subtracting.
Yeah, you could do a condition. You could say that would definitely work. You could say, well, if I ran the con tool and said, if this equals this, show me the difference, or if this equals this, just make it 1, or like if you were just interested in where the sinks were, a condition might be the better one, right? Because if they don't equal each other, tell me, right? You could, though, even replicate it, but you still have to do the subtraction problem to get the subtraction. So to answer the question that I ask individually, exactly right, would be minus, or we could do it in a raster calculator. We could do it either way. Both of them work. Okay, so the filled one is always by definition going to be higher than the other one. So if we want positive numbers, we put the filled one before the other one, and we run that. It goes through, and look what we got. We've got a bunch of zeros, a value of 3. So in other words, it had to fill it up 3 units. Remember, it went from 36 to 39. And then this one goes 2 because it went from 37 to 39. See how that works? All right, that was just a little like side question type of thing. We don't really need this data set, so I'm going to go ahead and remove it. I'm going to hit save just in case. All right, so going back to the workflow here, the next step in the process after we calculate the fill sinks is this one, the flow direction. So,
Dr. Raybert?
Yeah.
I don't know if anyone else had noticed this, but Aaron had just pointed this out to me. So when I was doing the flow direction manually in that little grid, I was using the paper that you had referenced from 1988. And actually, ArcGIS has a different orientation of their flow direction values.
Okay.
So I didn't know if anyone else ran into that, but me and Aaron just ran into that.
Okay. Well, yeah. So since we're working it out by hand, the importance is you know what direction it was in, right? Like that's not going to affect, like, however it's coded isn't going to affect the subsequent steps, because the subsequent steps are just going to use those values. So yeah, let's look at that though real quick. That's this one. Yeah, because this one starts with 1, and the other one starts with 128. I mean, ends with 128 right here, and 1 is right there, right? Is that what you're saying?
Yes, and so yeah, it changed. So those values in that paper are actually oriented differently than what ArcPro has them. So they're actually different directions based on which which one you use, the paper versus our pro.
Well, it's not different directions, so it's just different numbers. Like, I guess what I'm trying to say is here 2 represents due east. And
Right, but if you
GIS 1 equals 2.
right, yeah, so ArcGIS 1 is due east.
right, but it's still due east. Like, in other words, the people in the paper were just presenting a method, and ArcGIS happened to implement it slightly different, but it has the same effect. The water's going to flow east. So it doesn't really matter what you put right here. You could put the other numbers or the other numbers. Now you won't actually see the correct answers here unless you do it the way ArcGIS did it. But what's important is that you understand what direction it's flowing. It's gonna produce the exact same result in terms of the flow accumulation, because the flow accumulation is just all of the values that flow into there, and so you're gonna have to reinterpret these values into which ones flow into which ones, and you'll get the exact same answer whether or not you coded them this way or coded them the way ESRI codes them. Does that make sense? Like it's not going to change the end result. Like if you use these numbers to mean in other words, if I'd put 4 here, as long as I knew that 4 meant this direction, then I'm going to do this right. I'm going to say, okay, well, there's one cell that flows into that one. See what I'm saying?
Yeah, I see what you're saying. I went ahead and did it with the program before I did it by hand, so that's why it threw me off.
Okay. Yeah, I could see that. I would. Yeah. I'll change the lab to make sure that people understand that those differences. Yeah. I anticipated most people would use the lecture slide rather than the article, but I could see where that caused some confusion. But I wouldn't change your answers. Just make a note that you used the Jensen and Dominique article rather than that. Okay. You're going to get the same thing, but you are going to have to, like when we run this next step, this flow direction step, if we click the filled DEM, let's just go ahead and do this. So, and then I'll mention what I'm talking about here. So I'm just going to call this worksheet flow direction, and then make sure you click force all edges to flow outward. In practice, this rarely matters, like force, because usually you're dealing with a raster that has hundreds of thousands of cells, or at least tens of thousands of cells, and so just those little like 1 cells on the outside aren't going to matter much to your problem. In practice, I don't often check that, but you should. I mean, it really doesn't make sense not to check it. You should recognize that it's really impossible to predict whether or not the cells on the outer edge are flowing any direction. So we're just going to, this basically says ignore the outer cells. All right. So then we can optionally input the drop raster. Like if we actually wanted to be able to go verify our calculations in terms of which one, like why that a particular one was the lowest one, we could output another raster here. I'm not going to do that this time. So I'm going to hit run. Okay. All right, once I get my answer, this is the flow direction raster. So these two were both 2s. Now if you coded it the way, what I was trying to get at, Shara and Aaron, is that if you coded it the other direction, you would have to recognize that a 2 in ESRI is really the same thing as a 4. So it's the direction that the water is flowing out of the cell. So we were correct in both of those cases. Right? And here we get a value of 1. And so if we went back to here, we might assume that it's going in the northwest direction, but it's not. It's going in the west direction because we're using the ESRI scheme. So you have to convert between the two. Incidentally, how could we convert between the two? That might be kind of an interesting question to solve, but there probably is a mathematical formula that we could do to do that. We might have to do a condition statement. We could say condition, if it's 1, make it 128. If not, then because what are these numbers anyway? 1, 2, 4, 8, 16, 32. What's another way to say what those numbers are? The powers of 2, right? This is 2 to the 0. This is 2 to the 1. This is 2 to the second. This is 2 to the third. 2 to the fourth, and so on. So the reason, if you read through the paper, and I'll just go ahead and say it now, that one of the reasons that they chose these values to code them is that you could unambiguously model water flowing into multiple cells if you desired to do that. So, in other words, a 2 and a 4 and an 8, when you combine those two, 8 plus 4 plus 2 is 8 plus 4 is 12, 13, 14 is 14. And so there's no other way you could get 14 besides an 8 and a 4 and a 2 because of the powers of 2. So that's why they chose those values. If they weren't trying to do that, in other words, if they were just trying to model just the one direction, they could have made them 1, 2, 3, 4, 5, 6, 7, 8, 9, or 7, 8.
So, can it flow into multiple? It can flow into multiple.
Not using the D8 algorithm, but you could use the flow. Well, so yes, not using the D8 algorithm, but this method could be applied to other algorithms that flow into multiple cells.
Well, because on the grid that we have, the 39 and oh wait, there's 36. Never mind.
Yeah, I tried to make it so there wasn't any ambiguous. Now, if there are areas that have the exact same slope, ArcGIS does. If we read the help here, it tells what it does, because that is a good question. Like what? So if we switch to MDF, if we switch to multiple flow direction, then it would use the same coding formula, but it would code it differently. Okay. Here I'm sure for adjacent cells across a flat area, the result is the map. There's got to be some way. We're calculating. Yep. Let's see. I already covered that. Anyway, what happens when they're equal? It doesn't say. But ArcGIS does have a way to handle it when they're both equal. It picks one. I think it like might look upstream or something, but we're not going to look at that right now. All right, so that's the flow direction grid cell, and we verified it with these two, and we think we're right. And then we would move on to the next one, which is the flow accumulation. All right, so flow accumulation needs the flow direction raster. I'm just going to call this one flow there we go. All right, so this is what your flow accumulation looks like. And it's the number of cells that flow into that cell. So the highest value here, well, the highest value here is 10. We're not going to use that value. We're going to use this. Okay. So that's 6. What does that represent? What does that value 6 mean in the flow accumulation raster?
There's 6 cells that flow with it?
Right. There are 6 cells that flow into it. So hopefully you got that when you calculate it up by hand, or you will get that when you calculate it up by hand. Okay. But we could see here that that's a value, that's got a value of 6. That's the direction that it flows out. But what cells flow into that cell? Well, we go back up here. So it looks like this cell flows into there, and that cell flows into there. So if we look here, this is a 2, which we know is that direction. This is a 1. Okay, so that's actually flowing. Never mind, that I was wrong. That's flowing that direction. That flows that direction. Okay, so that flows this direction. What about that one? 40 to 39. Now that one flows 4, which is south. Okay, so it's only that cell right there that's flowing into this cell. But then we need to find out all the other cells that flow into it, because there's evidently just 6 of them. So these 2 are both flowing into that one. What about these 2? Well, that one's flowing into that one. So, now. Yeah, I used the filled one. Exactly. Okay. All right, so that's the way you can calculate flow accumulation from that. Okay, now we do want to calculate we do want to show you how to calculate watershed real quick, because the watershed is necessary to do this last calculation over here. And so we need to find out where the watershed is. So there's a tool called watershed. And if you notice that one of the inputs is a raster or feature pour point data. And I didn't know this. This didn't exist. This didn't exist in older versions of ArcGIS Pro even. But now it looks like you can actually interactively choose your pour point. So here, if I say, okay, I want to do my flow direction raster, and I want this point right here to be my pour point, just select in it. Okay. Then I can rename this just worksheet watershed. Worksheet watershed. And then run it. All right, well, I guess my interactive one isn't working like I thought. Because that didn't work. Now sometimes it's really finicky about where it puts it. So let's try this. So I often have to run snap pour point to get my pour points to match up with a particular raster. So I'm going to take the watershed pour point thing and use that as input, and then specify that I want to use a particular flow accumulation raster. And what it does is it will actually color the cell that's closest to this, that has a distance that's within a certain distance. So I'm going to change this distance to 100, because actually I'm going to change it to 50 because I know it's close enough. If I change it to 100, it might actually choose this one, because this one also has a really high value. So I'm going to run that. And you can see, wow, it didn't, it's not really working. I don't know if I like this one. Let's create a pour point the old-fashioned way. I mean, let's create our watershed the way that I'm familiar with. So I've been trying to use this, right? What if we wanted to create our own pour point? Well, we can do that. We can go into catalog, and I don't know if you, Well, you guys probably didn't use ArcGIS Pro. Who used ArcGIS Pro for the introductory GIS class? No? Okay. So I think it's actually even easier to create new data in ArcGIS Pro than it is in ArcMap. So you can go to a location that you want to put a new data set in. By the way, I already have this pour point in here, but that pour point is for this other data set. So I'm going to right click here on the Hydro Lab and say that I want to create a new, actually I'm going to click on I'm going to put it in the GDB. Databases. Yeah. I'll put it there. So I'm going to say new shapefile. I'm just going to call this shapefile pour point. And I'm going to make it a point. It doesn't actually have to be a point. It could be a polygon. And then I'm going to run that. I don't need to change anything. I could say that I want the coordinate system. I'm just going to leave it at the default, so it just chooses for me. Because there's really no coordinate system here. It's a fake coordinate system. All right, so now I'm going to take my pour point data. And I'm going to put it right there. And so I go into edit, and I choose create, and then I click on pour point, and then I pop my pour point down in the middle of that area, and I finish it. And then I have to make sure that I hit save. Save all edits, yes. And then I'm going to close down the editor. I'm going to make sure there's nothing else selected. So now I manually selected that. I still might have to snap the pour point, but let's just try creating a watershed from that. Let me try it real quick. You don't have to try it yet. So I got my flow direction. I got my pour point that I just created, and my output raster. I'm going to delete this one and call it this. Okay, so I was able to place it close enough that I didn't have to snap the pour point. But if you run it and you get something that looks different than this, you'll need to snap the pour point to get it. And that's especially true on the second part of the lab, the big one. Okay, you need to run snap pour point because there's so many cells that it's hard to choose the exact right cell. All right, so this area represents the watershed. All these values have a value of, all these areas have a value of 0. Okay, and all these have a value of no data. So what we're going to do is use this as a zonal statistic once we bring in the other raster cell, this one. So we have this one. We have to get that one and then do the zonal statistics. All right. Is anybody interested in seeing how I would do that, or do you guys think you could do that yourself?
I'm interested in watching.
Okay. All right. So what we want to do is get the answer to how much water is flowing out of here, right? So what we need to do is do the same thing we did earlier. We need to get our annual rainfall and put it in a file. And I'm going to save this as, instead of elevations.ascii, I'm going to save it as precip.ascii. I need to make sure that I say all files. So hit save. Now I've got this other precip layer saved. Come back in here, and I change this value to copy raster again. And then I have to do that same thing. Actually, you know what might be easier? This is something that's often helpful. Is if you go all the way out of geoprocessing, no, not all the way out. There. If you go to the history tab, you can see I ran copy raster earlier. I can double click that and open it up. So now I'm in copy raster. Now I can just change, because I know this is going to be precip. I got to make sure that I change the name. This is going to be worksheet precip. If I don't change the name, then it'll overwrite it. And run that guy. So here's my precipitation. Okay. So you can see that more rain falls down here than up here in this grid. Okay. This, of course, this is just made up data, but that's the way that you would, or actually the opposite of what I said. Less rain falls here than up here. All right, so I'm going to do it in the raster calculator, like I did before. Raster calculator. And this time, in order to get the precip value, I'm going to say in order to get the runoff value from the precip, 0.51 times, which one? Worksheet precip, plus or minus 336. That. So I'm multiplying those two together, I'm getting it, and then I'm subtracting it. Order of operations will take care of it, so I don't need parentheses. And I want to save this as, I'm going to call it precip, worksheet precip. Worksheet precip. All right, so remember we said this was going to be those are different. That's a different value. Let's make sure, because that's 123. This is 900. 900. Because we want to compare. Oh, it's because I changed it. Okay. So I was moving on to another one. So with 900, it is the right number. 123. Yep. 123. So that works. Okay. All right. So now I want to ask the question: how much water runs off to this point? Worksheet precip. So I'm going to put the watershed up here. I'm going to recode the watershed value to be, yeah, yellow is good. Okay. So in other words, I want to sum up the values that are underneath the yellow cells and find out what their total is. And I do have to do some unit conversion here it's not too difficult, but there is unit conversion. So right now, my problem is my cell size are in meters, and my depths are in what? Millimeters. So there's no wrong answer to the way you do this. But first of all, now you don't need to do it first, but at some point you need to mix the meters up right. You need to make sure the meters aren't mixed up right. So you can either calculate the zonal sum and then figure out how many meters that represents. But before, when I said you multiply by 100 by 100, you actually wouldn't. You'd actually multiply by the number of millimeters times the number of millimeters times the number of millimeters. And it would just be a ridiculously large number. So now I'm thinking about it, I think that it would be actually easier to convert the runoff into meters first before we even do the zonal statistics, or do it after the zonal statistics. Convert that millimeters to meters at that point. So actually, it it'd be the less calculations because we wouldn't have to do it. To do the zonal statistics first, turn it into meters, and then come up with a number. So, should we do zonal statistics? Why are we doing zonal statistics? Why are we doing zonal statistics? We're trying to find the total runoff in the yellow areas. So anytime we're trying to find a statistic about an area, it's a zonal operation. So we're calculating the what's our zone data going to be? Our zone data is the area.
So the zeros?
The watershed, right?
Right.
Yeah, which is zeros. Okay. So then the value field here, it doesn't matter. It is possible to delineate more than one watershed. Like you could have 2 points. You could put a point here. Oh, I should do it on here. You should put a point here, and you could put a point over here. You could delineate 2 different watersheds. And if your points were coded, if this point was coded 1 and that point was coded 2, then the watershed for this one would be coded 2 and the watershed for this one would be coded 1. All right? But most of the time you're just delineating one watershed, and ours was coded 0. This is where it got the code from, by the way. It got the code from there because we told it to use the ID field. All right, so we're going to take these values and do a zonal sum. That's why we're doing a zonal sum. What's the value raster going to be? What are we trying to sum up?
The amount of flow in those cells or precip in those cells?
Yeah, the amount of precip, but not the precip. We really are only interested in how much runoff there was, right? So precip's close, but it's actually the runoff.
It's that worksheet precipitation.
Oh yeah,
You didn't call it runoff.
I didn't call it runoff, so I messed up. So let's yeah, it is this one. This is actually runoff. You're right. Thanks, Shara. It's the runoff. I'm going to go back to history, and where's my raster calculator where I did the operation, and it should be worksheet runoff. It's not a big deal. Like it's just my name that I labeled it, but I don't want it to be called precip. I want it to be called runoff. So I'm going to delete this other one that I created before. All right. So now when I go back here, zonal statistics table, I can select to do the watershed and then the runoff. Okay. All right, so I'm just going to call this watershed stats, and I could make it so that it's all of them, but really I'm only interested in the sum. So I'm going to run that. And once that's run, I don't get anything new on the map. It's a table. So open it up here, and I have for all the areas that were 0, there were 8 of them. This is the area, and that's the sum, the entire sum. Now the problem here is that this area is in meters, and this sum is in millimeters. So if I want to get meters, if I want to change the units, I need to change this value into meters. So I'm going to add a new field. I'm going to call this sum underscore meters. Make that a double. Hit save. Go back here. All right. I'm going to calculate that value. How do I convert millimeters to meters?
Multiply.
What's that?
Multiply.
I could. I think it's a little more. I mean, multiply and divide are really the same thing. But remember, this is millimeters. So so I could multiply it by what, 0.001 or something, but I'm going to divide it by 1,000 because that also works. So this is right now it's in millimeters. I divide it by 1,000. I'm going to get it in meters. Okay, so that's my meters. That's the total runoff in meters. Okay. So basically, I have a bunch of cells, and they've each got some millimeters of water in them, and I've basically, if I could freeze it, I'd have 100 meters by 100 meters by some millimeters, and what I've done is effectively stacked all those up, and the total of stacking all those 8 cells up with their 158 millimeters and 123 millimeters is 1.31 meters tall. Okay. So if I want to find out what the volume of that water is, it's 1.31 meters tall, and it's 100 by 100 meters wide. So I could add another field, call it total runoff. I'm also going to make that double. And then it's going to be, that's fine. All right. And then my total runoff here, I'm going to calculate that field. And see that the field name is total runoff, and the value will be the meters value, and spell meters right off the R, times 100 times 100. That's going to be in cubic meters. So I'm cubing that value. Length, width, height, I got it. So that is the total runoff in cubic meters for those 8 cells for that year. Okay. Now, we did kind of a basic thing, but we could answer all sorts of environmental questions with this. Like, let's just say we had runoff just for a particular, like we had precipitation just for a day, and we could model the runoff for a day. We could find out how much runoff we expected to be at a particular point on that particular day, how much runoff there would be. We didn't talk too much about flow length, but we could use the flow length back to every cell to tell us at what point we would expect to see those different levels of water. Like, in other words, at this time we'd expect to see this much water, and this time in terms of volumes of water. And so we can answer the question, like let's say there was a culvert right here. So we're trying to answer the question, is the culvert going to be big enough? We could do that by breaking the question down into math, like really simple math, but it's still math. All right. So anyway, that's the way that works through. Did anybody get to that point yet so far? Does that match what you got? I don't know if anybody got to that point. But anyway, as you calculate it out by hand, you should get that value. Okay. So what are you going to do for part 2? Well, part 1, you're going to do that, and then For part 2, okay, you model your function chain. Yeah. I didn't actually do this as a function chain. I did it by hand. So here you can either draw out the process that you did to get to the question. It's important that you understand the steps that you took. I want you to say, I started with this, these were the inputs, this was the output. This was the next thing that I did, these were the outputs. So that's why you need to either draw it out by hand, or you can actually build it here in Model Builder if you wanted to. So if you go to Analyze, you could build it out in Model Builder, or you could run this as a function chain. Now, if you run it as a function chain, the pour point will be a little bit different. You'll have to convert the pour point to a raster to do that. And I can show you how to do that real quick, so that if you wanted to do it as a function chain, you could. You would say point to raster. So if you say point to raster, you could feed your pour point in, and you could feed it either the FID or the ID. It really doesn't matter because there's only one of them. And then all this you can leave default. However, the cell size, you want to make sure that you make the cell size the same as the input. In fact, I don't even think you want to change it here, because what you really want to do is make sure that the processing extent is the same as one of your other layers that you've created. So we can go with any of them, literally. Okay. And then you want to make sure that the cell size is the same as any of them, really. You want to make sure that the snap raster is the same as any of them. Okay. Once you make sure that those 3 values are the same, then you can hit go, and your pour point raster will turn into that. See how that's a raster? Now you can use that in a raster function chain. So here, if I go up to, because in the raster function chain, everything has to be rasters. It doesn't mix raster and vector. So if I go in here and I did watershed, it's going to ask for a pour point. My pour point raster, I'm going to choose the one I just created. And then the flow direction raster, I'm going to choose the flow direction one that I originally chose. Pour point value, that's fine. I'm going to run it. It should produce the exact same result, and it did. It's black still, but I could change the symbology again. So now it looks exactly the same. These two, this layer and this layer, look exactly the same. So there's no difference. Well, okay, there is a slight difference. Oh, it's because I have this on. Never mind. There's no difference. Okay. All right. So that's how you could create it as a. That's how you could do it as a raster function chain if you wanted to. All right. You got a question? Sorry. All right, so you're going to follow the exact same process through, except for I will warn you that you will need to do a snap pour point in there. But you're going to follow the exact same purpose through with some downloaded data. So let me talk about this, and then we'll take a break. We're going to kind of do the opposite. So today we did the lab first, and we're going to take a break, and then we'll talk about the. We're basically just going to talk about the test as the lecture content. All right. So here's my new map, and I can add on this other data, the hydro data that I downloaded. So I've got my DEMs. I've got my precipitation. So this is actual precipitation from a time period. I actually don't remember what time period it is, but we've got actual precipitation map, and we've got a digital elevation model. Okay, this is the Hattiesburg area. So what we're going to do is follow the exact same process through. We're going to fill the sinks. We got to do the flow direction, calculate flow accumulation. Okay, you're going to do each of those. The only thing different is that I also have another data set called impervious. This is Hattiesburg. And this percent impervious represents how much water, this is simplification, but it represents how much water could be absorbed by the land at that particular location. So it's a function of vegetation and land cover type and soil. Okay, so that's what we see here. So if I click right here, the percent impervious is 14. If I click right here, the percent impervious is 59. In other words, it's not very impervious, relatively speaking. Some of these areas, like in downtown Hattiesburg, are even higher, 78. There's the mall, the Turtle Creek Mall. That's 99. So we're like talking the top of a building or something. Okay. So we're going to calculate runoff a little bit differently here. We're going to take runoff is going to be calculated as the impervious layer divided by 100. So it's going to basically turn it from a percent back into a ratio, and then multiply that by the precipitation layer. In other words, this layer, instead of having a single value everywhere, we're basically saying, okay, well, some runoff would be different. Runoff would be different in some areas than it would in other areas. Okay, so this is a function of how much. This is just a ratio, and it's a function of how much precipitation would run off. Now, in reality, some of the implications that happen is that as the land saturates, you'll have more runoff, and so this is just an approximation. Like if you actually want to do this, you could run a temporal model where you ran this multiple times at different time steps. We're actually going to do that later in this course, but it's not for a water model, but you could do it for a water model. All right, so that's that. Anybody have any questions about what you're doing? You're following the same process through that we just went through, except for you don't have a watershed yet, but this pour point right here is zoom to layer. It's right there. Let's turn. Okay. Did I say download the data and pour point? You will have to modify your process slightly. I didn't say to do snap pour point, but you should do snap pour point here. Okay. Just before you run your watershed. So it does. I didn't find that really well. Let's see. There it is. So here you got just before you run your watershed, run snap pour point. That's where that goes. In fact, we could do that together real quick. So feed it our pour point. Our pour point field is going to be ID. Well, there's only one, so it doesn't matter, but if there were multiple, it would. And then we need our flow accumulation raster. Oh, we haven't calculated flow accumulation yet. So yeah, to calculate flow accumulation, you have to do fill sinks, then what? What's the next step? You have to fill the sinks and then calculate flow direction. And flow direction is the input to flow accumulation. So flow accumulation is now the input to snap pour point. So yeah, that's why you have to run each of these. So you're gonna run flow accumulation. You're gonna run all those processes, but yeah, you just.
I know we run that on precipitation. Sorry. Like when there's just 3 clouds. I'm trying to think. Like when we do the accumulation.
Right. So we're modeling flow off of the surface of the Earth. So we're filling the sinks in what data set? We're modeling flow off of the surface of the Earth. Let's think. It's raining on the Earth. What determines where the water flows for the most part?
Elevation.
Elevation, right. So the DEM. So we take the DEM, and that is the input to fill sinks. Fill the sinks. The output is what out of that fill sinks? What could we call that output? Yeah, it's the filled DEM. So it's still elevation, but now all the pits are filled. Okay. Then the next step is we take that that filled DEM, and we run flow direction on that. Okay. So what's the output of the flow direction? That's even easier. The output of flow direction is flow direction, right? So we got a flow direction raster. Then we run flow accumulation. And flow accumulation, the output is, again, easy. It's the flow accumulation raster. Okay. Then we could run snap pour point. And snap pour point needs the flow accumulation as the input and also needs our pour point as input. And all it'll do is it'll adjust that pour point a little bit so that it's right on a stream. Okay. Then the next step is that we run watershed on the snapped pour point and the flow direction raster. It needs to go back to the flow direction raster. And so then you'll have that watershed, and that's going to be your zone. Now, you're doing a different process now. Now you have to calculate runoff, and runoff is this formula here. Not that formula. Is this formula here. So you just take the impervious layer, divide it by 100, multiply it by the precip layer, and you're going to get runoff per cell, and then you're going to calculate the zonal statistics of that watershed. How much runoff is there for that entire watershed? That's the question you're answering. How much runoff is there for the entire watershed? Okay. Now remember, you are still gonna have to do some finagling because no. Oh yeah, the units are different this time. So the precipitation units are in inches. So this is even a little bit more difficult, but it's only more difficult because you have to use a different formula. So when you calculate the zonal statistics, it's going to be in inches, and you need to convert that to meters first. So how do you convert inches to meters? There's a formula. You just look it up. You just type into Google meters. Sorry, it's going to be inches. Inches to meters. So you multiply it by 0.0254 instead of we divided it by 1,000 in either. So if you go back and watch the video, the place where we divided by 1,000, you multiply by 0.0254, and you'll get meters out of inches. So when you first do the zonal sum, it'll be in inches, and we want meters. Then you'll have to multiply it by the cell size, which now is 30 by 30. So it'll be the answer that you get there times 30 times 30. I'm talking about this part right here. So you're going to get a zonal sum. We divided by 1,000 to get that. You're going to multiply by this 0.0253. Right? Yeah. You're going to do the same thing. You're just doing it differently because the units are different. Then, how do we get from here to here? Well, from here to here, I multiplied by 100 times 100. Now I'm going to multiply by 30 by 30 because that's the cell size. So the algorithm, in other words, algorithm is just a fancy word for recipe. The recipe is the same. Recipe is already a fancy word for a set of instructions, I guess. A set of instructions. Set of instructions is the same, but you fill in different values. So here we're going to go from 100 times 100 to 30 times 30, and we get that value. That's your answer, your total runoff for that watershed. But you're going to do it for this watershed over here, right? Any questions about that? All right.
Hey, Dr. Raver?
Yeah.
For the second part 2, are you just going to use the snap 4 point with that point feature, or are you going to convert it? Or raster?
Well, it depends. You'll get the same answer if you do it in Model Builder or in or as a raster function chain, but you have to convert it.
Okay.
Raster function chains only accept rasters. You have to convert it if you want to use a raster function chain. But I didn't do this example in raster function chains, but we could have. All right, any other questions?
So on part 2, where you have the new formula for the impervious and precipitation, right?
Yeah.
Shouldn't it be? So I ran it, but where it's not impervious, it has 0, so it changes everything to 0. So I've changed it to 1 minus the impervious layer. I don't know if it's.
Let me see.
So like when I just ran it as is, everywhere where there was no block to the water went to 0 for runoff. Because they're labeled 0.
Yeah, so okay, so if they're that does make more sense. Because right now it's percent impervious, right?
Right.
So like out here we get a value of 0, and 0 becomes 0, so nothing runs off. Yeah, you're right. I gotta change that. 1 minus. I'll change that. Actually, yeah. I would put a parenthesis around that too. Thanks, Avery. All right. And then the other thing that I was going to say was here. Coding scheme that. All right, we can take a break. I'm just going to type up. Just going to type up this answer. I mean this thing, and then upload it. So there'll be a new version. But this is the thing that Shara pointed out earlier. I don't know how to spell dominate off the top of my head. Let's come back at 10 after. And we'll be done today by 4. I'm just going to go over the test and some of the types of questions that'll be on there. Courses.